So, today we're going to look at trigonometric addition and subtraction formulas, etc. Let's see how much of the etc. we get to. So, I have kind of some meta comments here. Hand out all these? No. I'm going to do something I don't do very often. There's a reason. Is the right one? No. I'm going to risk, I probably do this every day, I'm going to risk either scaring you or putting you to sleep, one or the other. I'm going to show you a proof, and I know it's probably difficult to follow. It's kind of arcane looking, but I'm only going to do one like this, and I think it's valuable because it ties things together. So you don't need to you don't need to worry about reproducing this for the exam. All the steps are all well within your grasp. It's all basic geometry and algebra. You might ask, where does this? How did someone think this up? Where did it come from? And the answer is, I don't know. A lot of times in math, you're doing a proof and everything is just, after you've done math for a while, it's like really obvious. Oh, that's how to get from point A to point B. But sometimes you just see something that's kind of cool and you go, oh, wow, who came up with that? But in particular, what we want to do is we want to find out what the cosine of x plus y is in terms of simpler sines and cosine functions. And as I say, it's going to take a little mental energy to get through this, but let's go for it. So we're going to start with a unit circle. Big unit circle. And we're going to label this point over here A. And you might as well write in its coordinates, 1, 0. And next we're going to pick kind of an arbitrary point P in the first quadrant. And we're going to draw a radius. And we're going to label this arc here R1. That is to say, the measure of that arc is R1. And here it would be useful to go down memory lane and remember way back when you were taking geometry that if you have a central angle like this, the measure of this angle is the same as the measure of the arc. So this angle is going to be R1. Okay, that's pretty simple. Next, we're going to pick another arbitrary point we're going to call Q on the circle. And again, draw a radius. And now we're going to label this arc between Q and P, we're going to call that R2. So of course this angle here is going to be R2. And finally, we're going to pick a third point, R, but R is not arbitrary. We're going to pick R so that this arc here is also R2. Now, I guess it might be worth noting at this point that the angle from the axis to R here is minus R2, right? It's in the negative direction. Okay. The way this proof is going to work is we're going to take a look at two chords. Chords, remember what a chord is? It's a line between 2 points. We're going to draw two chords here, QA and PR. And first I'd like to establish geometrically that they are the same length. All right. So the arc QA has length what? R1, not length, but measure R1 plus R2. And the arc from PR also has measure R1 plus R2 for, I think, obvious reasons the way it's been constructed. So there's a theorem in geometry that says you have a circle, the lengths of the chords, right, are going to be equal if the measures of the arc is equal. And so our derivation here, our proof, is going to center around the fact that these two lengths are equal. Before we go on to doing that, I want to label the coordinates. So Q, we have the angle R1 plus R2. So the coordinates of Q will be cosine R1 plus R2 sine R1 plus R2. Similarly, the coordinates of point P, since we have an angle R1 here, will be cosine R1 sine R1. And finally, this point R, it's going to have coordinates cosine minus R2 sine R2. All right. So you don't know how we're going to get there, but you see where we're going now. The question is, how do I, given the coordinates, how do I determine the length of one of these chords? What am I going to use? I asked earlier, will the exam cover just what we're doing now, or will it cover everything? said, well, somewhere in between, something from the earlier part of the exam could come up, but here it is coming up right now. What do we use to find the distance between 2 points? It's kind of a duh question when you hear the answer. What formula do we use to find the distance between 2 points? The distance formula, yes. Well, remember x1, x2, y1, x1, y1, x2, y2. The distance is x1 minus x2 squared plus y1 minus y2 squared. Right? So let's get that going. So first, QA, we're going to equate QA to PR. So the distance QA is what? It's going to be cosine R1 plus R2. Coordinates of A are 1, 0, so minus 1 is squared, plus sine of R1 plus R2 minus 0 squared. Okay, that's good. And now we need to know PR. So that's square root of, pardon me, cosine R1 minus cosine minus R2 squared plus sine of R1 minus sine of minus R2 squared. Okay. Everything else is algebra. Some heavy lifting, though. All right. Let's do some things in place. We can get rid of this minus 0 thing right away, right? We just have sine squared here. Cosine of minus R2. I'd like to simplify that. What's cosine of R minus R2 in terms of just R2? We need to use an identity that we looked at in the last few days. Do you recall? If you're not going to help me, it's going to take longer. What's the cosine of minus x?
Positive cosine.
Cosine of x, yeah. Yeah. Why is that? Why is the cosine of minus R2 cosine of R2? Yeah. It's an even function, right? Cosine, even function. What about the sine of minus R2? It's not an even function. It's the other one, yes.
Negative sine of R2.
Yeah, it's negative sine R2. So if I want to make this positive, I'll have to take that minus out. This becomes positive. Okay, that's a good start. I think we want to square both sides. Right? You can just imagine I've erased that line there. And let's expand these and see where we go. Okay? So this is cosine R1 plus R2 squared, minus 2 cosine R1 plus R2 plus 1. That's this part here. That's just using a plus b squared, or a minus b squared. And we just have sine squared r1 plus r2. Okay, again, I have to expand this. So we have cosine squared r1 minus 2 cosine r1 cosine r2 plus cosine r2 squared. That's this part, expanded. And here, what do we get? We get sine squared r1 plus 2 sine r1 sine r2 plus sine squared r2. Okay. This is the kind of algebra we all like to see, right? Lots and lots of stuff. But it's hard to get anywhere with all this stuff on the board. So it'd be nice if we can simplify this a little. And there's some obvious simplifications here. Cosine squared r1 plus r2 plus sine squared r1 plus r2 is what? 1. It's 1, right? Sine squared plus cosine squared is 1. Okay. What else have we got here? Cosine squared r1 plus sine squared r1. It's also 1. That's nice. Cosine squared r2, sine squared r2, that's another 1. All right, so let's do that. This is 1. We've got another one here, so it's 2 minus 2 cosine r1 plus r2. And what's that equal to? Well, we've got a 1 here and a 1 here, so that's 2 minus 2 cosine r1 cosine r2 plus 2 sine r1 sine r2. All right. But the 2's are going to just drop, aren't they? That was really fast. We're not quite done. Let's divide through by minus 2. So cosine r1 plus r2 equals cosine r1 cosine r2 plus sine r1 sine r2. That's our formula. Let's write it over here. Cosine x plus y is cosine x cosine y. Oh, I made a mistake. I made a mistake here. Oh, when you multiply that, divide by minus 1, that becomes minus. There we go. Minus sine x sine y. Right, so we have our first formula that tells us the sum of cosine of x plus y in terms of sines and cosines of x and y. We're going to have a lot of formulas coming up. Trying to memorize them is kind of a difficult endeavor. Some of them are useful to keep in your head, especially if you're going on to calculus, because we're going to use these formulas to do simplifications, substitutions. What you want to keep in mind is there's some patterns here. I'll point them out. But there's some patterns that simplify this long list we have into a smaller list. show you what I mean in just a second. First, let's clean up here. Okay, the next formula we want to look at is cosine of x minus y, the subtraction formula. You're going to see that we did the hard work. Everything else we're going to do is fairly simple comparison. See, we can look at cosine of x minus y. That's just cosine of x plus minus y. And we have a formula for cosine of x plus y now, so let's apply that. Right? It's cosine of x, cosine of minus y, minus sine of x, sine of minus y. But we can simplify this again using our odd-even identities. Cosine of minus y is just cosine of y. Sine of minus y is minus sine of y. So we have a minus and this becomes a plus. So we have sine x cosine y plus sine x sine y. These are so similar that we'll usually write them as one by doing the following. We'll say cosine of x plus or minus y. But over here we'll say minus plus, so you don't get them confused. You either use the upper or the lower. Okay, so now we have two formulas. Let's go ahead and see what we can do about sine of x plus y. Well, I'm sure there's somewhere there's another elaborate proof where you draw some chords on a unit circle. But it's unnecessary because somehow the formula for sine x plus y is somehow embedded in this. In particular, I know that the cosine of 90 degrees minus x is what? This is another identity we look at, a cofunction identity. Anyone recall this? Yeah.
Sine theta.
Sine x. Yeah. I was using theta. What about sine of 90 degrees minus x? What's that? Yes?
Cosine x.
Cosine x, right. We have a whole series of cofunction identities you should know. So how are we going to apply this? Well, we want sine of x plus y. But according to our identity, that's cosine of x, cosine of 90 minus x plus y, which I want to rewrite this way. I want to rewrite it as cosine of 90 minus x minus y. But I have a formula for that. Right? Recall cosine of x minus y. I can use that here. So let me go ahead and try that. That's cosine of 90 minus x times cosine of y. And remember now, because this is a minus, for the cosine it's a plus, so I have sine of 90 minus x sine of y. Okay? Well, but these are just cofunction identities, aren't they? This is sine of x cosine of y plus cosine of x sine of y. Aha! It's kind of a different pattern, right? In one case we have cosine, cosine, sine, sine. Here we have sine, cosine, cosine, sine, right? Good. I really like the fact that we did one really weird and difficult proof. Everything else that's going to come out of it is relatively easy. Same thing we did with cosine of x minus y, we can do with sine of x minus y. That's sine of x plus minus y. Is sine of x cosine minus y plus cosine x sine of minus y. But again, these are our odd and even identities. Cosine of minus y is just cosine of y. Cosine x. Sine of minus y is minus sine of y. So I get a minus here. And it looks like I can write this very conveniently. Sine of x plus or minus y. Sine x cosine x plus or minus cosine x sine y. Let's at least see some reason why this might be kind of useful. What if I asked for the cosine of 75 degrees, but I don't want that decimal expansion that your calculator is going to come up with. I'm not going to be able to write it all down because for two reasons. One, the calculator is going to round off. If you had some super calculator that didn't round off, you have to write down an infinite number of numbers. But I want to know exactly what 75 degrees is, cosine of 75 degrees. Well, you notice that cosine of 75 degrees is the cosine of 45 degrees plus 30 degrees. Well, there's some hope here. This is going to be cosine of 45 degrees times the cosine of 30 degrees minus the sine of 45 degrees sine of 30 degrees. And each of these are special angles that we know exactly. Okay, cosine of 45 is 1 over the square root of 2. Cosine of 30 degrees is square root of 3 over 2. Sine of 45 is 1 over the square root of 2. Everybody's keeping up with me, right? We all know these. writing on the back of your hand now, right? What's the sine of 30 degrees? 1/2, yeah. So we end up square root of 3 minus 1 over 2 square root of 2. As you know, I'm not big on rationalizing denominators, but we've got radicals top and the bottom. Let's do that. So that's square root of 6 minus square root of 2 over 4. Wow. See, before we just knew, what, 30, 60, 45, 90, and all those multiples. Now we can find multiples of 75. If you think about it, I could just as well have subtracted these, right? And I'd have the cosine of 15 degrees, right? Cosine of 45 minus 30. That would be a plus. So now I know the cosine of 15 degrees exactly. And any combination I can come up with. Now that I have 15, I can add 15 to 15 to 15. Gives me 30. I guess we don't really get anything new. Now we're down to multiples of 15, I guess. We're not done, though, with that. We'll be able to go a little further. All right. We found these formula for the sine and cosine. It shouldn't be a big stretch now. We go for the tangent. That's because we know the tangent is just the sine over the cosine. And we have formulas for the sum of the sine and cosine. Sine of x, cosine y, plus cosine x, sine y, over cosine x, cosine y, minus sine x, sine y. Well, it's a formula that's not the most elegant. But we might be able to improve on this a little bit. If we multiply by 1 over cosine x cosine y over 1 over cosine x cosine y, a name for 1, what would we get? We get sine x cosine y plus cosine x sine y cosine x cosine y over cosine x cosine y minus sine x sine y over cosine x cosine y. Well, here my cosine y drops out, and I have sine x over cosine x, so that's tangent of x. Here I have cosine x sine y, cosine x over sine y. The cosine x drops, and I have sine y, cosine y. So I have tangent of y. Did I do that too fast? It means that. Here I'm crossing out cosines of y, so this is tangent. Here I'm crossing out cosine of x, so I just have left with the tangent of y. Over here now, cosine x, cosine y, cosine x, cosine y, that's just 1. Sine x, sine y over cosine x, cosine y, well that's tangent x times tangent y, right? I group the x x's and the y's. So that's tangent x, tangent y. Okay, so I'm completing my formula list here. Now I have to think for a minute. I want to do that same trick I did with the sine and the cosine function. I want to find out what tangent of x minus y or plus minus y is. But I need to know, is the tangent an odd or an even function? Tangent is sine over the cosine. It's an odd function divided by an even function. Does anyone recall what kind of function the tangent is? Yes?
An odd function.
It's an odd function. So when I go to minus, well, tangent of minus y is going to be minus tangent of y. And here, tangent of y again is going to be, tangent of minus y will be minus tangent of minus y. So this will become plus. Oops, write it that way. Plus. So plus minus, minus plus. Okay, these are pretty useful formulas. Again, there's 6 formulas there, but if you see the pattern, there's really only 3. And probably the hardest thing is to keep these 2 straight, because they look a little different. And now I can find exact values for tangents and sine and cosines of anything that's a sum or a difference of something I know. Or that you know. All right, we're going to do one more thing with these. It's more than anything, we're going from complicated to simple now. These are the sum and difference formulas. We want to look at what are called the double angle formulas. And they pop right out of what we've done. I want to find the cosine of 2x. Well, that's just the cosine of x plus, I'm sorry, yeah, cosine of x plus x, which we know to be cosine x minus sine x, or cosine squared x minus sine squared x. Turns out this formula shows up, is going to show up a lot in calculus when you're doing calculus on trig functions. Let's write this down here. Cosine of 2x equals cosine squared x minus sine squared x. Where it shows up is you do some kind of calculus-y thing, differentiate differentiate or you integrate. And then you have kind of a mess left over. You want to simplify, and so this might come in handy. However, sometimes it would be handier if instead of having cosines and sines, you had just one of them. Just cosines or just sines. Well, it turns out that's really easy. That's really easy to accomplish here. You may have noticed how much this already looks like a certain identity, the Pythagorean identity. So we could just add to this sine squared plus cosine squared minus 1 because what is sine squared plus cosine squared minus 1? 0, yeah, you can add 0. But that makes this look a lot nicer. This is now, the sines drop out and you get 2 cosine squared minus 1. So this is an alternate way of looking at cosine of 2x. It's 2 cosine squared minus x minus 1. But we could just as easily added 1 minus sine squared x minus cosine squared x, because sine squared x plus cosine squared is 1, 1 minus it is 0. Only now, when we simplify it, we get 1 minus 2 sine squared x. So it's actually useful. Again, you don't have to memorize it. You can, if you want to memorize this, but remember, it's easily transmutable into one of these forms. We actually will have some problems where that actually comes in useful. All right. Okay, so that's the double angle for cosine. Double angle for sine, not quite so flexible. All right, it's going to be sine x cosine x plus cosine x sine x. Well, that's just 2 sine x cosine x. Not much else you can do with that. I know this shows up a lot in calculus. You'll end up with this, or you'll end up with this, and you'll just want one function, and then you go, aha, that's sine of 2x over 2, right? Comes up a lot. All right, let's just complete this. The tangent of 2x would just be, according to the formula, tangent x is tangent x over 1 minus tangent x, which is just 2 tangent x over 1 minus tangent squared x. Okay. These formulas don't bias that much in terms of calculating new values. already know for everything we know exactly, like 45, but we know 90, 30, we know 60, 60, we know 120. So they're not that useful for those purposes. But they are going to be very useful, aside from, these substitutions I mentioned, when we go in the other direction. We're not going to do that today. I'm going to stop here early. No. Okay. We're going to pick up from here on Wednesday. Any questions before I let you go? I'm not really letting you go. We're already packing. All right. See you on Wednesday.